Insulators are used widely in air-insulated substations to keep personnel safe and prevent the electrical energy leaking out. By the end of this section, you will know all about the different types of insulators we use inside air-insulated substations, and learn about what the creepage distance is and how it affects the design of the equipment inside the substation. The aims of the course today are: look at the different types of insulators that we use inside air-insulated substations. See how we select insulators. Introduce the idea of creepage distance and learn how we use it to design insulators. Insulators are used throughout substations to carry the live conductors and to separate them from the grounded structures that carry them. The main types of insulators that you find inside substations are post insulators. These carry the conductors and bus bars that connect all of the equipments together. Support insulators. These carry the line conductors and keep them a fixed distance away from the grounded gantries and structures. Cap and pin insulators. These are used to connect the live line conductors to the grounded structures that hold them. And finally, bushings. These contain a live conductor inside them and are used on circuit breakers and transformers to keep the live conductor away from the grounded housing. The two main things we need to consider when using insulators are the structural strength to carry the conductors during normal and fault conditions, the ability to withstand the potential voltage difference that appears across them. The structural strength required is defined by the forces on the conductor, which we've already looked at in the previous section. So let's now look at the potential voltage difference requirements. Insulators are constructed from materials such as ceramic, epoxy, and glass that have such a high resistance the electrical energy cannot pass through them. Most insulators have a positive voltage potential on one side, caused by the live conductor or busbar, and a zero potential on the other side, caused by the grounded structure. The aim of the insulator is obviously to withstand this voltage difference without breaking down. All high-resistance insulator materials achieve this goal without any issues. However, the main issue we face is not electrical energy passing through the insulator, but passing down the outside. This effect is called tracking and is shown above. As we can see, the rectangular shape gives a direct path for the electricity to flow, which is really easy to break down. By increasing the linear distance that the electricity needs to flow from the live side of the insulator to the grounded side of the insulator, we make it more difficult for tracking to occur. We increase the linear distance by changing the shape of the insulator. Instead of the squared insulator, which is fairly easy to break down, we normally use this shape. As we can see, this revised shape means that the distance that the electricity needs to flow around the outside of the insulator has increased substantially. The distance around the outside of the insulator is called the creepage distance. The minimum creepage distance depends on the weather and environmental conditions, something which air-insulated substations are particularly vulnerable to. The electrical utilities define minimum creepage distances, based on the likely environment that the insulators will be subjected to. Here's a typical table showing the minimum creepage distances for various situations. Category 1, where we have slight contamination, will have a minimum creepage distance of 60 mm per kilowatt. The highest category, Category 4, is in areas with heavy industry, where we're susceptible to dust, fog, and sea air. In this condition, the minimum creepage distance is double the Category 1 distance, and is 31 mm per kilovolt. A utility will define the creepage distance for the whole substation, depending on its location and the local environmental conditions that it operates under. A good example is a transmission substation connecting a coal-fired power station to the high-voltage network. Most power stations need to be located near a reliable supply of cooling water. If this happens to be by the sea, then we have a double issue of pollution conditions from the coal-fired power station, together with the salty sea air, which may result in a high creepage distance requirement, and the need to wash down the insulators on a periodic basis to prevent a breakdown. Let's do a worked example. We want to use the following cap and pin line insulator to attach a 400 kV overhead line to a gantry structure in a Cat 3 environment. Calculate how many insulators we will need. As we can see, the insulator has a creepage distance of 720 mm. Here's the answer. From the table, Cat 3 creepage distance for an industrial area with pollution equals 25 mm per kV. The line voltage equals 400 kV. But what's actually being applied to the insulator? Well, it's not the line voltage, it's the phase to ground voltage. Therefore, phase voltage equals 400 kV divided by root 3 equals 231 kV. Therefore, the creepage distance required equals 231 kV multiplied by the Cat 3 creepage distance, which is 25 mm per kV, equals 5,775 mm. Our single insulator has a creepage distance of 720 mm. Therefore, number of insulators equals 5,775 mm from above, divided by the single insulator creepage distance, equals 8.02, i.e. 8 insulators. Okay, we don't want to go below this level. Let's make it 9 insulators to give us a bit of insurance. When a new insulator design is created, it is type tested to ensure that it can meet the demanding electrical conditions imposed by the basic insulation level and switching impulse level voltages. These tests are performed under both dry and wet conditions and follow a defined procedure as per the IEC standards. All insulators are also subject to routine testing to ensure the integrity of the insulator and identify any voids that may be present inside the ceramic or polymer material. During these tests, the leakage currents are measured to ensure that they fall within a defined range. One of the main types of insulators that you will see inside an air insulated substation are post insulators. Post insulators are used to carry the conductors and bus bars as they pass from one piece of equipment to the next. Here's a typical post insulator. It normally consists of 3 parts. Firstly, we have the palm, which is at the top of the post insulator. This holds the conductor in place and can be specified in many configurations, depending on the type of clamps or conductors being used. Here we have a flat palm, which allows clamps to be bolted on both sides. We then have a spigot-type palm, which allows the clamp holding the conductor to be fixed at one point. The next item is the insulator. As we've discussed, the higher the creepage distance, the longer the insulator will be. And finally, we have the base of the insulator, which allows the post insulator to be fixed to the structure below. Next we have the structure, to carry the post insulator and raise it to the required height off the ground. This height is defined by the electrical clearances, which we'll look at in a later section. The structure is usually a galvanized steel lattice structure or a tubular aluminium pole. Sitting below the structure, we have the pad-type foundation, which is sized to carry the weight of the structure, the insulator, and the bus bar. The foundation also needs to handle the mechanical forces exerted on the bus bar. As we've seen in the previous section, these can be significant. The horizontal spacing between the post insulators depends on the type of conductor being used. Solid and rigid bus bars don't sag in the way flexible conductors do, and the spacing in between the post insulators can therefore be increased. The face-to-face spacing between the post insulators depends on the electrical clearances between the bus bars. As the system voltage increases, the electrical clearances increase, and so does the distance between the post insulators. Most post insulators are made of epoxy resin or ceramic materials, which provide the insulation level required and the physical strength to carry the conductors during normal and short-circuit conditions. Line insulators can be made of glass, ceramic or polymer material, and they are designed to carry the tensional forces exerted by the line conductor. As the system voltage level increases, you will see that the length of the insulators also increases due to the creepage distance. The final category of insulator that you'll see in air insulated substations are bushings. Bushings are different to the types of insulators we've looked at so far, as they contain a conductor. Typical examples include equipment bushings, say for use in transformers or circuit breakers. Wall or air bushings. These are used to take conductors from inside a building to outside a building. Here's a typical circuit breaker, with bushings being used for the three-phase inputs and the three-phase outputs. The bushings allow the live conductor to pass through the grounded enclosure and to provide a clearance distance from the enclosure to the live conductor at the top of the bushing. Bushings are designed to have the same creepage distance as all the other insulators inside the substation, as they suffer from the same environmental and pollution constraints. Let's summarise what we've learned today. Insulators are used throughout air-insulated substations to carry the live conductors and to separate them from the grounded structures that carry them. The minimum creepage distance of an insulator for an air-insulated substation depends on the environmental conditions. The more pollution we have, the higher the minimum creepage distance. The horizontal spacing between post insulators depends on the type of conductor. The space between the different phases of the busbar depends on the electrical clearances. Congratulations for completing this section. You should now be able to identify the different types of insulators that we use inside air-insulated substations, and understand what the substation creepage distance is and how it affects the design of the equipment. I have attached some questions on today's section to test your knowledge.